Hey guys, it's Caryn with the Need Project. I'm coming to you live from Central Indiana, and my husband Jeff is manning the phone today, so I have my hands free. We're going to be doing a nuclear candy chemistry activity, so I'll just kind of give us some time for some people to get started here. Jeff, if you can kind of keep an eye on that and kind of nod your head when people are joining, that'd be great. Also, I forgot to tell you this, Jeff, we have to know how many people are on at the end of it. So the supplies you're going to need today are some long, narrow candy. I'll be using a Twizzler pull and peel strand. Teachers, if you're looking to do this with your class, one strand is all each kid needs, and this package has 12 bundles of 9 strands. So there's 108 pieces in here that your kids can use. So when I did this with my kids, with my teaching, I only had to buy 2 packs of this, and there were extras. The other things you're going to need are 100 pieces of candy that have a mark on them. So I'm using M&Ms. You could use Skittles because they have an S. If you don't have the candies, you can get 100 pennies because those are heads and tails, or anything that's got 2 different sides that is flat, that you can pour out of a little cup. You're also going to want to have a knife of some sort. So I would suggest a butter knife. It doesn't have to be sharp. And you'll need some graph paper. You'll need a ruler or a measuring tape and something to write with. Then an optional thing is if you have a kitchen scale around that measures in fractions of a gram, that's great. I have this little balance that we use with our Science of Energy kit. So I know this measures fractions of a gram, so we're good to go there. Give you guys a couple minutes to get your materials gathered up. Today's activities are coming from our nuclear energy curriculum. So we have exploring nuclear energy and energy from uranium. Energy from uranium is our middle school level or intermediate level, and exploring nuclear energy is our secondary or high school level. So the 2 activities, I printed one from one book and one from another book. So Licorice Decay, that is in our intermediate level. And then the M&Ms activity is in both the secondary and the intermediate. I guess I did print the intermediate for this one too. Okay, cool. So I want to talk to you a little bit about what is radioactivity and what is a half-life, and then we'll jump into it. So here's our periodic table, and I drew a line right here. This pink line is the dividing line between things that are not radioactive and things that are radioactive. So anything larger than bismuth, so starting with polonium, these elements are naturally radioactive. Now, what does radioactive mean? It means that it emits particles because the nucleus is too big to be stable. So when you start cramming protons and neutrons together, there's a limit to how many you can cram together. When you get to more than 83 protons, those nuclei are no longer stable and they start breaking down and breaking apart. Okay? I drew a blue line down here after uranium because uranium is the largest naturally occurring element, and everything bigger, starting with neptunium, plutonium, americium, and so on, those are all synthetic. And then I drew a line over here around technetium because that's also a synthetic element, plopped right there in the middle of all these naturally occurring ones. Okay? So that's what radioactive just means. It breaks up and emits particles. Doesn't have to mean a dangerous thing, although radioactivity is not usually something you want to play around with. There's radioactivity all around us every day, in the rocks and in the air. It's just the amount of it that can be the dangerous part. So let's talk a little bit about what a half-life is, because this activity simulates a half-life. So I've shown some half-lives here. Okay, the shortest one is an isotope called radon-196. It only has a half-life of 4.3 milliseconds. So to give you an idea of how long a millisecond is, when you blink, that's 150 milliseconds. Okay, so this is much, much, much shorter than the blink of an eye. And a half-life means that when you start with a certain mass, after one half-life, you have half of that mass left. So if I started with 100 grams of radon 196, after 4.7 milliseconds, I would only have 50 grams of that. And then another 4.7 milliseconds, I'd only have 25, and so on. Okay? So as you can see, some of these isotopes are very, very short-lived. Fluorine, 1.83 hours, that's not very long. But come down here to uranium-238, that's 4.5 billion, 4,500 million years. In other words, as long as the Earth has been around, uranium-238 has been around, okay? Some of these other ones have shorter half-lives ranging from milliseconds to seconds, hours, days, and so on. So isotopes that are not stable can have short half-lives or long ones. The other thing I want to point out is you see some elements that are smaller than our 83 for bismuth, carbon, sulfur, and fluorine. An isotope is an arrangement of protons and neutrons. This is still a carbon atom, but instead of having 12 protons and 12 neutrons like almost all carbon atoms have, 6 protons and 6 neutrons. This has 6 protons and 8 neutrons. So it's got too many neutrons and it's not stable. That's why it's radioactive. Sulfur here has 16 protons and, gotta do this math in my head, 19 neutrons. Okay, a regular sulfur atom has 16 and 16. So this one is too big to be stable. So sometimes we have elements that we're familiar with that are also radioactive. Carbon-14 is naturally occurring. We use that to date things that are, you know, maybe made out of leather or wood, or a paleontologist finds a preserved mammoth and wants to know how old it is. They'll use radiocarbon dating to figure that out. And some of these other isotopes like phosphorus-32 are used in medical research. All right, so that's all there is about half-lives. Just a little bit of information. Remember, a half-life, when one half-life occurs, half of the mass is gone. Okay? All right, let's start with the licorice. So I've got my instructions. I have my graph paper. Jeff, if you could tilt down so everybody can see my graph paper, that would be great. Thanks. I'm going to start, here's my measuring tape. I'm going to start with one piece of my candy. Okay? So I'm going to measure the length of this candy in centimeters and just make a note of it. And I'm also going to take the mass. So my candy is 21.9, that's not right, 21.4 centimeters. It's right here. 21.4 centimeters. Reading upside down and backwards is not easy. All right, so I'm going to just make a note of it. 21.4 centimeters to start. And now I'm going to use my balance and take the mass of my candy. It wants to fall on the floor. All right. Sit there, be good. Down there. You can't read that. I gotta turn it around. 3.8 grams. Okay. All right. 3.8 grams. It's okay to just hold it up and keep it still. Thanks. All right, so this is our starting mass, okay? So this piece of candy represents our starting material and what we're going to begin with. What I want you to do, I have enormously large graph paper, okay, so that you can see it on camera. We're going to be working, this is our x-axis, and this is our y-axis, okay? On our x-axis, we graph our independent variable, the thing that can stand alone. So down here on the x-axis, we're going to mark that as half-lives, okay? All right. So we're going to start over here at 0 half-lives and lay the candy right up on that y-axis, okay? Get it lined up nice and perfectly, make it nice and straight, and put a dot right at the tippity top of that candy, just like that, okay? Now I started on the axis, on the y-axis, because this is 0 half-lives. We're starting. We haven't done anything yet, okay? All right, so I've laid the candy. This is my mass of my starting material. Now I have my candy. I'm going to take it and I'm going to fold it in half like this. Okay, notice that I've got my ends lined up. Take my knife, cut it in half, put half to the side or eat it. I'm not a Twizzler fan, so I'm not going to eat it. Now, 1 half-life, I'm going to skip a line, and 1 half-life is going to be 2 squares. Okay? So I'm going to put my candy right there. This is my first half-life, so I'm going to label that 1, and I'm going to put a dot. All right, so is 0 half-lives. I started with this. 1 half-life has gone by, and I have now half the mass that I started with. Okay? I'm going to take my candy. I'm going to fold it in half, just like this. Come on, crease. And put half of it aside. Skip a square, go down here. Make my dot. All right, so this is going to be, I can't do a 2 upside down. This is after 2 half-lives. Okay? Take your candy, fold it in half. This is where my hands get in the way. Take my knife, cut it, put half of it aside, skip a line, make a dot. I'm at 3 half-lives. Are there any questions popping up, Jeff?
Not as of yet.
Okie doke. Now, 3 half-lives. So I've cut it. I'm down to here after 1, here after 2, here after 3. Okay? So next is going to be 4 half-lives. I'm going to take my candy. I'm going to fold it in half. I'm going to take my knife and cut it. This is why you don't use a sharp knife, because you're getting kind of close to your finger. Put half of it aside, lay it on my graph paper, make sure it's lined up nice, make my dot. I think I could do this one more time, okay? You're going to fold and cut until you have a piece that's too little to fold and cut. Cut it in half one more time. Yeah, I'm not going to be able to fold this in half anymore. Not going to happen. Put half of that aside. I'm over here at 5 half-lives. Lay my candy down. Put my dot. There. Okay. So now I have what looks like a graph, right? And this graph is showing the mass of the candy after a certain number of half-lives, okay? If I were to connect my dots, starting here, we get a curve that looks like that. All right, the other thing I want to do is I want to now measure the mass of that little tiny piece that I have there after 5 half-lives. And it's measuring, come on, you can measure that. Okay, we're going to say it's less than 0.1 grams. All right, I'm going to also measure it. So put the measuring tape back. I'm not going to measure it starting at my 0 mark on my measuring tape. It's got this brass piece that's in my way. So I'm going to measure it starting at the 1 centimeter mark. Where is it? Oh, I'm going to start at the 2 centimeter mark, because the 1 centimeter mark is covered up. Get back over there. Why is it when you want things to work quickly, they don't? All right, I'm lined up, okay? I'm at my 2 centimeter mark, which is really my 0. So I'm going up to, looks like 6 millimeters, right? Not quite. Could estimate. It's between 5 and 6 millimeters. So I'm going to say that it's at 6 millimeters, which is equal to 0.6 centimeters. Okay? Get that little bugger out of the way. Get this out of the way. Now, the reason that oops, I can't talk and do this at the same time. Come on. Okay. The reason I wrote down these numbers is because we started with 21.4 centimeters, so 21.4, and we ended up with about 0.6 of a centimeter. So I'm going to divide that by 0.6. I should get a half, a quarter, an eighth, a 16th, a 32nd. I should get about 32. And I got 35, okay? Now, that's not perfect because my folding and cutting technique wasn't perfect. But I cut it in half 5 times. So I divided in half once, twice, 3 times, 4 times, 5 times, okay? So my expected was 32. My measured was 35 times smaller. Does that make sense? All right. So that's the licorice decay, okay? And what that shows you is that it's giving you a graph of how radioactivity works. A half-life goes by and we have lost half of our original mass. A half-life goes by again and now we've lost 3/4. And now we've lost 7/8. And now we've lost 15/16. And then we've lost 31/32, okay? The big question for you is, how many half-lives does it take when we have nothing left? And that is a trick question because we'll never get down to 0. It'll just keep getting closer and closer and closer and closer, but it will never cross that line, okay? If we were able to accurately cut that Twizzler in half every single time. All right, that is half-life with a Twizzler or a nerd's rope or a piece of string or whatever else you find lying around that you want to work with. Now, let's look at it in another way, okay, using our M&Ms. I still need my board so I can write. All right, so I have my instructions. The instructions are to have 100 pieces of candy or 100 M&Ms, and you can kind of tip up a little bit if you want to so that I'm in there. If you want to sit down again, that's cool. Yep, there we go. Awesome. Okay, so I have my M&Ms in my cup. I took out the yellow ones because the M's are difficult to see on yellow candies, at least when you're old like me. Maybe if my friend Marianne is watching and you want to use the yellow M&Ms, you go for it, Marianne. All right, so we've got 100 of our M&Ms or our pennies or our Skittles, or I think you could maybe use Sweet Tarts. I don't know if they have a marking on one side and not the other. So we're going to start 0 half-lives, just like we did with the Twizzler, where we started on the axis. We're going to start at 0 half-lives. This is our original sample. The M&Ms are representing our original sample of a radioactive element, okay? So at 0, there are 100 M&Ms in here. All right? So the next thing we're going to do is we're going to dump them out, and we're going to sort them out. I want to take out all the ones that have the M facing up. Those are the ones that have decayed. You can choose the M's facing down if you want to. It doesn't matter. As long as you do it the same way every time, that's okay. All right? So you just got to sort them out. Pull out the ones that have the M facing up. Set them aside. Almost there. This is where having a lab partner is really helpful. M&Ms with the M's up. And now you can see why we pulled out the yellows, because it would be really difficult for me to find them. And I got 2 more. Oh, there's one. All right, all I have left, these are the ones I'm going to set aside. I don't want those. All I have left are M down. So now I'm going to count them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. No way. That never happens. So we expect that we would have half. I've never done this where I have exactly half. Never happens. So yay, hooray for Instagram Live, right? So after one half-life, we have 50. That's what we would expect because we cut them in half. But I'm telling you right now, it never happens that way. All right, so now I have my 50. That's what I'm going to start with. And now I'm going to dump them. That'll be my second half-life. So I'm going to put a 2 in my box. I'm going to dump them out. Spread them out. Take out the ones that are M side up. Keep going with taking out the ones that are M side up. They're getting sticky. Also, teachers, if you do this with your kids, and if you have them bring their own candy samples and they're handling them, that's fine. If you're going to have your kids do this, what I used to do is it was just once a year. I would just buy a boatload of M&Ms. I would have the ones that they were handling and dumping on the desk and getting their hands all over and making a mess with. And then I'd say, here you go. Here's another cup of M&Ms that you can go ahead and eat. I don't know what, depends on what your policies are at school about whether they can eat things or not. That's why it's nice to use pennies sometimes because it's not a heavy investment. Kids aren't going to eat them. They're not sticky, that kind of thing. Okay. Now, I took out the ones that were M up. Let's count what I have left. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, 24. We would have expected to have 25 because that's exactly half. Pretty doggone close, guys. So we're going to put them back in. The first dump is the slowest and it gets faster from there. So now I have my next sample, and I'm going to go into 3 half-lives. I'm going to write a 3. Spread them all out. I think I just turned some over with my fingers. All right. 1, 2, pull out the M. Sorry, I'm not counting yet. Pull out the M up. Leave the M down. Is that one up? That one's up. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll do this one more time. It'll be 4 half-lives. And I'll dump them, take out the ones that are M side up. And we have 4 left. Okay? If I went to a 5, what would you expect here? If you said 2, good job. So the next thing I want to do is I want to graph this. I've been using large squared graph paper just so you can see it on camera. That's not necessary. So Jeff, if you could tilt up again, I'm going to graph this. The first thing I'm going to do is label my axis down here for half-lives. And over here, I'm going to put mass. And that's in our unit of M&Ms. Okay? So 0. And I know that there are 20 squares from here to the top, and this is our 100. So we're going to start here, okay? And I know this because I counted them before I started with you guys. So I'm going to spread my graph out like I did before and go a 1 here, a 2 here, a 3 here, and a 4 here. And the reason I'm spreading it out so much is because I want you to be able to see it well on camera, but you don't have to do that. Okay. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Here's my 50. After 1 half-life, I had 50 M&Ms. After 2 half-lives, I had 24. 5, 10, 15, 20, 25, just a little bit less. There's my 24. And after 3, I had 10. 5, 10. After 4, I had 4. Okay? So I'm going to connect my dots. With nice perfect lines. That's a joke. Now, this is M&M decay. This is licorice. Okay? If they look the same, it's because they are essentially the same. All right? This one, our method was to cut in half. And this one, our method was to use a probability that it's going to end half the time heads or tails. Okay? This is what an exponential decay curve looks like. High schoolers, this is what it looks like. You're looking at something that's like this. Your formula, y equals 1 over 2x, where x is down here. Okay, so we're cutting in half 2 times x times. So we're cutting in half 2 times 1, 2 times 2, we cut it in fourths, and so on. Okay, exponential decay. All right. This is going to show you how things decay in real life. Go ahead, tip up. Perfect. It shows you how things decay in real life. It gives you an idea of half-life. How does this relate to you? Well, sometimes there are things that are out there in nature that are naturally radioactive. You don't need to be concerned about them because the half-lives of those things are pretty low. Or in the case of uranium, if you live in New Mexico or Arizona or Southern California, you might encounter some rocks that are higher in uranium than we have here in Indiana. And that's okay. That's just background radiation. So in that case, we're just looking at the amount that is present, okay? But the thing that this is really important is in nuclear power plants, when a fuel assembly is all done being used in the reactor core. So the material is no longer fissionable, it is run out of usable energy that we can use to generate electricity. The material is still radioactive. It's still giving off radioactive particles. And so that material has to be stored. How long does it have to be stored? You have to know what's in it to know how long it's going to last. Okay, and so because that radioactivity is so highly concentrated in those fuel pellets, it has to be stored safely and carefully. So half-life is important to the engineers who have to calculate how long things need to be stored in different places and moved, and how much exposure the technicians are experiencing as they're working with this material. Okay, Jeff, do we have any questions on the Instagram Live?
As of right now, there are no questions.
No questions. If you have any questions, now's your time to type it in. I will wait just a minute and tell you that if you're looking to download our materials, you want to go to shop.need.org, and on the left side is where everything is sorted out by subject. You just need to make an account with your information, and you can get all of our curriculum materials in a free PDF download. Then you can make as many copies of that as you need to. And keep in mind, teachers, if you have old copies of our materials, delete them from your hard drive, recycle the paper copies, and download new ones every school year, because we update those stats every year, and you'll have updated energy stats. Any questions coming in yet?
You have a well done thanks by CACERESLB.
Well, thank you very much. I appreciate it. If you need anything, just shoot us an email at info@need.org. We'll be glad to help you out with that. I hope you have a great day, and take care, everybody. Bye. How many people total?
14.
Okay.
It fluctuated.